So you were just investigating the sequence 1, 1/2, 1/3, and so on, and you were investigating using tolerances as we did in the end of the last clip. So let me just go ahead and recap for you what positions you would get here. So the first question, if you set the tolerance equal to 0.1, how far out do you have to go so that the whole sequence lies within 0.1 of 0? And so here, if n is greater than or equal to 11, then S sub n will be in. So this symbol here means in. So S sub n will be in the interval minus 0.1 up to 0.1. So this is the position that we're thinking about. If we decrease the tolerance to 0.05, then we have to go further out in the sequence. And so we actually have to go out to the 21st term. So if n is greater than or equal to 21, then Sn will be in the collar of width 0.05 around 0. So that would be from negative 0.05 up to 0.05. Okay, and so the tolerance for the two tolerances of 0.1, so if tolerance equals 0.1 and if tolerance equals 0.05, we can compute the corresponding positions with the sequence 1 over n squared. And so in the first case, what we saw was if n is greater than or equal to 4, then Sn is in, so this is now a new sequence here, but if n is greater than or equal to 4, Sn is in the interval minus 0.1 up to 0.1, and if the tolerance is 0.05, well, I didn't actually do it in the last video, but if you were to adjust the tolerance and look at the picture, zoom in a little bit, you would see that if the tolerance, if n is greater than or equal to 0.5, then Sn must be in the interval minus 0.05 up to 0.05. So what are you seeing here? What's the upshot of this comparison here? Right. If we're comparing for a tolerance of 0.1, we're comparing n must be greater than or equal to 11 in the case of the sequence 1 over n, and n it must be greater than 4 in the case of the sequence 1 over n squared. And then similarly, when we have the tolerance, you can see we're comparing 21 to 5. So what's the upshot of all this? Let me just go ahead and write here. Upshot is that the sequence 1 over n takes longer to converge. Than the sequence 1 over n squared. And you can kind of see that if you were to graph the function 1 over x and 1 over x squared, right? Let me just very quickly do this here. 1 over x looks like, okay, this is a cartoon of 1 over x, and in relation to that, 1 over x squared as you know, always lies below 1 over x, and so as you're going out towards infinity, 1 over x squared is getting close to the x-axis much more quickly. And so that's what we're seeing here very quantitatively with these computations you did in this exercise. All right, so I want to move on and talk about now how all of this relates to the definition in your text. So I just went ahead and copied that directly down here. So a sequence Sn will converge if there is some number L, the limit, so that we can make Sn get as close to L as we want by taking n sufficiently large. In other words, what we're saying here is that, so as close as we want, this is the tolerance, right? And so, in other words, there is some point in the sequence that's the sufficiently large n for which the sequence terms are all within that tolerance, and so that's where the tolerances are coming in, right? We're saying this n sufficiently large is the position for which all terms lie in the collar. Okay, and then if the sequence Sn does not converge, we will say that Sn diverges. So a sequence diverges if there is no L for which the tolerance game works. So let me go ahead and just write that down here, because negating this definition is actually, logically speaking, there's a lot going on there. So and I'm going to just colloquially say that so a sequence diverges if there's no L for which the tolerance game works. In other words, the sequence diverges. This is equivalent to saying for every number L, well, for every number L, let me just stick with the same colloquial description here. For every number L, the tolerance game doesn't work. And what I mean by that is any number L that you would choose, there exists some tolerance for which, no matter how far you go out in the sequence will always pop out of that tolerance. Okay, so the tolerance game doesn't work means here that for some tolerance, no matter how far you go out in the sequence, tail never stays in the collar. So, so what I'd like to do is maybe at this point, I'm actually going to go ahead and skip down. I think at this point, given this divergence statement, I think it actually makes more sense to do the your turn first, and then I'll come back to discussing the limit of an approaches infinity. So go ahead and at the conclusion of this video, go ahead and try to write down a statement of how you can describe the fact that this alternating sequence that goes 1, -1, 1, -1 diverges using tolerances. And I'd like you to go ahead and start with a graph. So start with a graph of the sequence and include some pictures as you in your explanation. Okay, and we'll discuss this example, and then we will move back up to the top of the page and conclude.